Thank you for the introduction. Again, my name is Yahui Chen. Today I want to talk about how we rewrite the ARM64 COTS binaries so that they can enjoy the protection of ASCII-only memory. This is a joint work between Stony Brook University and Samsung Research America. So the names in black are people from Stony Brook, namely me, Dongli Zhang, Rachel, and my advisor, Long Lu. And the names in blue are people from Samsung Research, namely Rowan Wang, Ahmed Azab, Hayo Vijay Kumar, and Wen Bosen. So first of all, what is ASCII-only memory, or ZOME, and why it is useful? So this primitive was first introduced by researchers from Stanford and UC Berkeley back in the 90s. They said that code contents cannot be viewed in the memory, and around that time they used ZOME to prevent software piracy. In recent years, ZOME has another calling, which is to help defend against the dynamic memory disclosure-based code reuse attacks, in which the attacker first leak a code pointer and then use a memory disclosure primitive to dynamically harvest the code gadgets, so that without any a priori knowledge about the binary layout, the attacker can assemble the gadgets and then hijack the control flow. So naturally, if we use ZOME to prevent the gadgets from being read, we can stop the attacker at step 2. And recent years, hardware vendors start to keep up. For example, in x86, you have EPT and memory protection keys. And in ARM64, you have ZOME directly configurable from kernel. And here is the earliest kernel patch that I found that tried to enable ZOME on ARM64 platforms. You can see that it dates back to May 2014, which is 3 years ago. So why after 3 years this primitive is still not massively in use yet? Well, it turns out one of the major reasons is that it's non-trivial to enable ZOME for COTS binaries. For example, in this figure, it shows the memory layout of the COTS binaries. And you can see that in this memory page, there are code and data interleaved together. And because ZOME can only be enforced at page granularity, that means all the data inside this memory page are non-readable, which will break the program. So a very high-level idea would be first you separate the code and data into different pages, and then you still need to properly update all the references, because if you miss any of the reference, this will break the program as well. Let me first explain why the memory layout looks like that. So basically, this is a legacy issue. Back in the old days, when people tried to make the ELF file standard, they did not consider read-only or ASCII-only and ASCII-only as incompatible. As a result, they put those read-only data sections together with the code content in order to get a more compact binary. In consequence, you have those ELF headers and those metadata sections such as GNU hash are placed together with the code sections such as PLT and text. Note that there are 3 thin orange bars inside the .text section that represents the inline data. And after the text, you have the read-only data sections and EH-frame sections. There are also read-only but placed together with those code contents. So other than the code data locations, regarding the references, for a normal ELF binary, you have intra-section references, intersection references, and lastly, you have even references from the external module. For example, the dynamic loader will want to access the ELF header and those metadata sections. So does the C++ runtime. That means by only examining this module itself, you cannot comprehensively resolve all the references. If this situation is not messy enough for you to scare you away from trying to solve this, what about there are still some unknown references from the external module? For example, in our experiments, we found that the Android R runtime wants to access the read-only section of the type of binary. So now let's revisit the high-level idea again. Firstly, you want to identify the executable data. Throughout the talk, I will use executable data as this term to refer to all the orange area inside this figure. So you see that because inline data are still prevalent in ARM binaries, so past research has shown that under such situation, telling data apart from code precisely is in principle undecidable. Regarding the references, hopefully I have convinced you it's very hard, if not impossible, to comprehensively resolve all these references. So facing such challenges, we made the following design goals for Norax. Firstly, regarding code data separation, we want to have analysis with very high precision we want to make practical trade-offs, which means that we want a superset of the executable data, but only a subset of the references, which will result in something like this. In this figure, the green ring represents the data collection results that we want, but on the right side, this small blue-grayish ring represents actually the missed references. So because of these trade-offs, we also have the security goal such that we want to expose as less code as possible, meaning that this green ring should be very small. And we also want to enforce this runtime security policy-based checks to tell apart the attackers from the legitimate missed references. And we also want Norax to be very practical by having low runtime and memory overhead. And Norax should not be exclusive to other COTS binary hardening solutions such as fine-grained code randomization and CFI. Also, Norax binaries should be backward compatible, meaning that the rewritten binaries, they can even run seamlessly on other ARM64 platforms, even without Norax support. And lastly, we want to enforce ZOM on a modular basis. So now let me show you the high-level Norax components and how they work together to achieve these design goals. First of all, we have this disassembler, which will collect the superset of the executable data as well as the intra-module references. And then these results will be fed to an patcher, which will calculate the new binary layout and then repackage the binary. And then this repackaged binary can be loaded by unloader during load time that will update all the collected references, also enable ZOM on a modular basis. You see that because we only update the references at load time, this again preserves the backward compatibility. And lastly, during runtime, we have a monitor as a runtime module that will handle the missed references as well as perform this access policy check. In this work, we use Android as our reference platform. Before I dive into how an disassembler works, I want to first share with you some background so that you can know the rationale behind an disassembler's analysis. First of all, in ARM64 ISA, they say that the instructions are all 4-byte aligned and has fixed size. Also, the PC register is no longer directly accessible, and most importantly, they only expose a very limited set of instructions to perform PC relative addressing. And this, combined with the fact that since Android 5.0, Google has removed the non-PIE loading from the dynamic loader, which means that if you have purchased your Android phone within the last 3 years, chances are that all the binaries inside the phone are position independent. So, bearing in mind these two observations, let's see how a disassembler works. First of all, it starts with a linear sweep, which will give us an over-approximate set of instructions represented by the green area. And then it does this what we call guided data collection. So remember, we observed that only a limited set of instructions can be used to collect obtain the PC relative addresses. And so we base our analysis on this limited set of instructions, namely the LDR literal and ADR ADRP. And we check the data load operations initiated by these instructions. So this will give us a very precise set of the data represented by these 3 orange bars in the green area. And then chances are that this set of data is still not complete because while we are checking the code, if we encounter some memory operations or indirect branch instructions that we cannot resolve, then we lost the check. In such situation, we mark the current tracking data as unbounded and then perform this unbound data expansion, which will expand the current check data backwards and forwards until we reach a valid instruction. By valid instruction, I mean that during the backward expansion, we stop at either the direct branching instruction with the valid targets or indirect branching instructions, which we will check the used register certified API property. And during the forward expansion, we stop at either the targets from a valid direct branching instruction, a valid branching instruction, or a set of function starts that we obtain using static analysis. So after this step, a superset of the executable data are collected. Then a disassembler will go ahead to collect the intra-module references, which could come from a list, this following list of sections. So for the sake of time, I won't dive into detail for this part, but in the paper we discuss what kind of program practice will result in the references from these sections. So if you are interested in this detail, please refer to our paper. And then this result is given to Ampatcher, which will calculate the new memory layout, specifically the new location of the executable data, in which process it also takes into consideration the reference addressing range, and it will emit a stub code to help access this relocated data, this new data location if necessary. And then Ampatcher will append the Norax related metadata to the end of the ELF. This again is to ensure the backward compatibility. So the Norax related metadata includes the duplicated inline data, the references locations and displacement, the stub code, and lastly the Norax header that can tell unloader where to locate this metadata. So during load time, unloader performs 3 of these subtasks tagged with LD1, LD2, and LD3. In LD1, it set up the Norax bookkeeping data, which I will discuss in the next slide. Also map the executable data to the new location accordingly. And in LD2, it redirects all the dynamic loader accesses to the new readable location by updating the dynamic session. And lastly, in LD3, it adjusts all the references and then enables zone on a modular basis. I want to show you how unloader works with this simplified program loading process. So first of all, you start with the executable loading. You can see we do LD1 and LD2 accordingly. And then the control flow is transferred to the dynamic loader, which will load all the dependence libraries. And for each one of the module, we also do LD1 and LD2. And after all the modules required by the process are properly loaded, the dynamic loader will go ahead to perform symbol resolution and relocation. And we do LD3 at this point. You see, we do it here because some of the references are only available during this time. For example, those from the GOT section. And by doing LD3 here, we have a higher coverage on the references. Lastly, the program can start and run. So if you have the question, what if the program load the library during runtime? You can see that because of our traces of timing to perform these 3 subtasks, this is naturally handled by unloader by doing this step 2 and step 3 again. So during runtime, a monitor will help resolve these missed references and also perform these default policy checks, And currently, we have a default policy that we made based on our experience, which we believe strike a very good balance between compatibility and security. Basically, the policy says that the code can only access this identified superset of the executable data region. Also, for the inline data, they should only be allowed for their hosting functions, which are these over approximated ranges that we obtain using static analysis. And lastly, for compatibility reasons, we mark the conventional file headers and those non-code regions as whitelisted for now. And on the right side, this is the bookkeeping data I mentioned in the last slide. So in this linked list, each node represents a module in a process. And you can see that each one of them has their own policy and whitelist, which will allow the need to adjust them if necessary. So we believe this policy does not hurt security for the following 2 reasons. First of all, even the attacker can read the executable data region. This part mostly contains only invalid data. For example, it looks like this. So they cannot be executed. And for the second reason, because of the policy about the inline data, now the attacker needs to use multiple memory disclosure bugs in order to explore the executable data in different areas. So now that I have finished introducing how Norax works, I want to compare it with a set of related works from the angle of how to enable zone. So in the first line of works, they enable zone by recompiling and relinking the program so that the binary emitted by the 2-chain when loaded will have code and data separated nicely. But it requires source code. On the second line of work, they provide a very handy static analysis to identify a subset of executable data, which is good, but it's not enough for our purpose. And we believe the most comparable work to Norax is HideM. HideM also wants to identify the superset of executable data. And here is how HideM works. So this figure, inside this figure, those green rings represent the function node of a call graphs in the program. And HideM starts from the entry point and then from this recursive disassembly and then also as well as some static analysis to identify this subset of the call graph. And then they mark everything else as data. You see that because of the limitation of static analysis, they inevitably will identify some code as data. So compare with HiDEM, these two works actually have their own advantages. For example, in the scope of ARM64, Norax is more precise because its analysis depends on specific ARM64 ISO knowledge. But HiDEM's approach is actually architecture independent. They can handle other architectures such as x86. And because of that, their disassembler is also robust against erroneous disassembly, which is naturally not a problem for ARM64 anyway. And Norax is more systematic because it has a higher coverage on the references, and also Norax is enabled on the real-world mobile systems. So I want to show you our evaluation results. So in our evaluation, we use 3 sets of the binaries. In the set S1, it consists of 313 64-bit system binaries. They are all stripped, dumped from the commercial phones, and we use them to perform our data analysis. And then in set S2, we select 20 of the critical system binaries, and then convert them, and then run our functionality test. In the last set, we use Unix bench to measure the runtime and memory overhead. So regarding the data analysis, so we use set S1, in which process we observe 132 out of 313 binaries has reported inline data. And 43 of them during the analyze process, they require this unbound data expansion, which means that the rest of the 132 binaries can be analyzed nicely with the guided data collection. And in this process, we also observe 28 of binaries has reported more, we have identified more code as data. But regarding the data missed, we do not miss any. But this is after we manually filter the unreferenced data such as the paddings and signature strings, etc. Because making them unreadable will not break the program, so we do not count them as false negatives. We also observe that in this, among these binaries, libm, libart, and libiq18 and the SOs has reported much more inline data than other analyzed binaries. And regarding the functionality test, we converted those critical system binaries, including the QCCOMD, the Qualcomm driver, and those important system daemons such as Zygote, install-D, service flinger, etc. They are used to support your day-to-day tasks such as launching up a new application, making phone call, or render frame buffer, etc. We also converted the low-level complex libraries such as libc, libm, and then we enable them, and during our functionality test, we did not observe any failure. Lastly, we run the Unix bench binaries. We converted them and then run them on this Qualcomm Snapdragon 808 chip with 2 GB memory, also known as the Nexus 5S phone. And we compare it with the original binaries. And in this process, we observe the average runtime overhead, peak memory overhead, and the file size overhead are all negligible. And notice that there's one benchmark, which is exact CL, that has much higher runtime overhead because this benchmark actually is doing a stress testing on the exact syscall testing. It just keep calling exec on itself, and this will trigger our bookkeeping data setup and keep triggering this locking unlocking mechanism. That's the reason why this exhibits higher overhead. So in summary, we firstly perform a systematic study of the code data separation problem on those COTS binaries. And Norax is the first comprehensive solution for enabling them on ARM64 platforms, in which it makes practical trade-offs to tackle the in-principle undecidable code data separation problem. It enhances the security such that it exposes very last code to the attacker and also enforces this runtime-based policy checks. And Norax features the practical design such that it supports the modular zone enforcement. It covers executable as well as libraries, and those common practices such as runtime library loading. And Norax binaries are backward compatible. You can run these converted binaries even on other stock ARM64 phones with seamlessly. And also Norax is non-exclusive, although I didn't discuss explicitly in the talk, but Norax does not introduce any change to the data flow and call graph property of the program. Lastly, we perform large-scale evaluation on real-world mobile system binaries, in which we show that Norax can precisely collect the data. Also, the rewritten binary incurs negligible runtime and memory overhead. So with that, I want to thank you for your attention and take any questions you might have.
So can you comment on the applicability of your techniques on x86, which is clearly more complex than ARM?
Exactly. So why we have the confidence to say that this can cover ARM64 is because of the specific ARM64 instruction set architecture, and because they only have this limited set of instructions that can be used to obtain the PC relative addresses, and this does not exhibit on the x86 architecture. So this is not applicable to x86.
Right. Right. Let's thank the speaker again.